Hello everyone and welcome to today's webinar, which is titled Musculoskeletal Modeling of Manual Materials Handling in the Danish Supermarket Sector. My name is Christopher Iversen and I'm from Anybody Technology, and I will be the host of today's webinar. Today I'm here with my colleague, Pavel Galiberov. So today we have an external speaker who is Sebastian Skals, who is a Ph.D. student at the National Research Center for the Working Environment at Aalborg University here in Denmark. And Sebastian is going to give his presentation in a minute or so. But just before we start, I will give a general introduction to the Anybody modeling system for those of you who is unfamiliar with the software or musculoskeletal modeling in general. The control panel appears on the right side of your screen, and you are very welcome to submit questions and comments via the questions panel, and we will try to address the questions in the very end of this webinar. And all the questions that we don't get to address in this webinar, we'll try to reach an email afterwards. But first of all, what is the Anybody modeling system? So the Anybody modeling system is a software that allows you to do musculoskeletal modeling. As input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint moments, joint reaction forces, and muscle forces. And here in the bottom of the screen, you see a screenshot from the Anybody modeling software. So this is actually how the system looks. At the moment, Anybody is used in a wide variety of areas and applications, and a few examples of this is movement analysis, product optimization design, sports, orthopedics and rehabs, and assistive devices. And the typical workflow in the Anybody modeling system could look something like this. So you provide the motion data as input, and you use the body models which you or others have built. Then you provide some kind of environment, which could be, for example, an exoskeleton. And then you can use Anybody to combine these things and run the inverse dynamic simulations to calculate the internal body loads. You can then output these results and use it for post-processing, which, for example, could be with some kind of finite element tool. But many users also closes the loop completely by doing some kind of design optimization and run this cycle multiple times. So this actually brings me to the end of the introduction, and I will give the word and presenter role to Sebastian Skals instead. So Sebastian, are you able to hear me?
Yes, I hear you fine.
That's perfect, and I think we see your screen as well.
Yes, just 1 second. Yeah, should be full screen now.
Yep,
welcome everybody, and thanks. Yes, thank you, thank you, Christopher. Yeah, welcome everybody, and thank you for tuning in for this webinar. I'm going to talk to you today about a part of my PhD project, which concerns the use of musculoskeletal models to analyze manual materials handling tasks in the Danish supermarket sector. This is a collaborative project between the National Research Center for the Working Environment here in Copenhagen, Denmark, where I'm speaking to you from now, and also Aalborg University. First up, I'll try to give you a little introduction to the work that we're actually analyzing here. And what we know here is that work-related musculoskeletal disorders are highly prevalent in the supermarket sector. And this is particularly to the lower back, the shoulders and the wrists, but also, for example, the feet and the knees. What we also know is that the majority of workers in the supermarket sector are primarily engaged in the receiving, stocking, and rearranging of groceries. Despite this, a lot of the intervention studies or biomechanical analysis of the work in supermarkets have actually targeted cashiers and check stands. But when we have been done observations for this particular project in the supermarket, we actually found that the majority of the workers spend almost all of their time in the handling of different groceries and merchandise, from the receiving in the storage room and to actually storing them and arranging them in the shopping area. However, not much is actually known about the biomechanical loads that these workers are subjected to during their daily work. As I mentioned before, the biomechanical analysis that has been made has been targeted cashiers, check stands, and also there's been done a little bit of laboratory studies with motion analysis and EMG, but finding field studies which use some kind of detailed measurements or modeling are quite rare, if they even exist. However, we know that manual materials handling in general is associated with the development of work-related musculoskeletal disorders, particularly to the lower back. So this was kind of our motivation to study manual materials handling in the supermarket sector in more detail. So when you assess the risk of injury during material handling or lifting, there's many different approaches you can take. And I listed some of the approaches here, ranging from self-reports, observational methods, direct measurements, for example, EMG or motion analysis, and also the use of biomechanical models. And of course, these methods range from pretty easy and cheap to get to quite expensive and complicated. So if you want to get something quick and you can use self-reports, you can go and observe. You need more detail, go to the direct measurements, get some muscle activity data and some motion, and use this input, for example, to analyze the loads using biomechanical models. So several ergonomic tools have been developed to assess the injury risk during manual materials handling, and some of the more famous ones are the NIAS lifting equation and also Snook lifting tables, but there are many, many more. And many of these ergonomic tools apply some kind of biomechanical model to estimate the joint loads. So what are the limitations of using these traditional style biomechanical models? The problem is that up until very recently, most of these models has been in 2 dimensions. They have been either static or quasi-static, meaning that you don't get the acceleration component and that get a true dynamic analysis of the actual motion. What that means is that, first of all, loads are only known for somewhat idealized lifting situations. One example could be the NIAS lifting equation, where it was originally designed to analyze lifting only in the sagittal plane with using 2 hands and with both feet on the ground. And it isn't particularly useful for analyzing very asymmetrical lifting and lifting that involves carrying and walking with the burden, for example. And another problem with using static or quasi-static analysis, it considerably underestimates the loads compared with dynamic models. So of course, we're interested in trying to apply some of the more advanced and dynamic models that are available today, for example, using the antibody modeling system. So what's traditionally kept us from being able to use these more advanced musculoskeletal models for this kind of purpose is that the information these models need to run is detailed kinematics usually, and also a measurement of external forces. And for everybody who made an experiment like this knows that usually this is done by force plates in a laboratory environment and using marker-based motion analysis, which in its current state is not feasible to apply in outside laboratory environments. So, but recently, there's been some methodological developments, one being that we are now able to predict ground reaction forces with very high accuracy, and also the development of this new inertial motion capture system from Xsense Technologies, which basically provides us with a sufficiently detailed kinematic data to be able to drive these models. And it also means that we can take our experiment outside of the laboratory and actually measure these kinematic data in a work environment, for example, or in any other sort of environment, and you do the full inverse dynamic analysis based on this information when we use this prediction method. So due to these developments, we saw an opportunity to try to implement these advanced models in the analysis of lifting and manual handling in the supermarket sector. So the basic aim of this project was to identify work tasks and ergonomic exposures that may pose a risk for the development of work-related musculoskeletal disorders in the supermarket sector based on state-of-the-art methods for inertial-based motion analysis and musculoskeletal modeling. First up, when you use a new methodology to analyze these loads, of course, you need to have an idea about how accurate this method is. And I just included this slide here to give you like a quick overview of the evaluation experiment we did. And there's a link here in the bottom left, which is a previous webcast, which explains this experiment. And there's a reference to a journal paper we did based on this experiment. So if you're interested in finding out more about this, check the webcast or read the journal paper. So back to this actual experiment we did here in the supermarkets. So as you can see here on the right side in the pictures, on the left picture, we have the setup we use to go around in the supermarkets and measure the workers. So on the left, you have this little rolling table with a laptop computer with wireless receivers for the inertial motion capture system, the XN system, and also a wireless receiver for the wireless EMG system, which was placed under this shirt you can see on the subject here on the right. And basically, we would start in the morning, follow the subjects around to some pre-planned lifts. So of course, we decided to include 12 common manual materials handling tasks, which is very common in the supermarket sector. For example, that could be the handling of boxes of bananas, milk crates, cucumbers, and then many, many more. Basically, we try to get like a wide variety of these different kinds of lifts you can see in the supermarket sector. And also, of course, trying to make it as realistic as possible under the circumstances of course, they're wearing motion capture equipment, they're wearing EMG, and it's a very stop and start kind of procedure. So we basically involved multiple start and end positions because there are many places you can store these groceries in the actual shop. There's different shelf heights and there's different starting positions they're used. And the starting positions are resembled here in the transport cage in the left-hand side picture. And later on, I'll be referring to low and high starting positions and also low and high shelf heights. And when I say low, it refers to this low on the transport case, there's the low and the high starting position here. And that's approximately 15 centimeters and 70 centimeters. So floor height and waist height, which also resembles quite accurately the starting position of a pallet, so a filled pallet all the way to the bottom of a pallet. So that would be the typical way they would store groceries in the shop, filling up this transport case with merchandise and going around the shop and filling up as needed. So in total, with all these multiple start and end positions, we ended up with 50 different lifting conditions, and we performed 4 repetitions per condition. So what you see here is another example in the fruit and vegetables departments where we prepared space to perform some lifting of bananas, cucumbers, salad, so forth. And you can also see the XSense window system on the subject, which consists of 17 inertial measurement units. And what my colleague on the left here is doing is perform the calibration procedure, which basically is a process of getting the subject to stand in a neutral position for some seconds, walking in front, walking back, and standing again in a neutral position. And this is quite an important step because this neutral position that you determine here is the is the, can you see from here, this is where all the joint angles are calculated relative to. So for example, if like the subject is bending their elbows a lot, or they're bending in the back or in the knees or so forth, that would be an error introduced to the actual measurements. And you see this, isn't it started? Okay, yeah, and as you can see here on the right, this Xsense avatar basically resembles that the subject is lifting a box to the end shelf height, and I was myself who carried the box back into place. And in that nature, we did the 4 repetitions. So based on this kinematic data from the supermarkets, we developed musculoskeletal models in the Anybody Modeling System 7.2 based on the BVH Xsense template from the Anybody Managed Model repository. And so the process is basically resembled here. You have the avatar, where you can export a BVH stick figure file from, and the scaling of this stick figure is based on manual measurements. So when you begin a measurement with the Xsense system, you have to use a caliper to measure certain body dimensions and input them into the software. But for this stick figure to be able to drive a musculoskeletal model, which has a different segment, different joint definition, we use this concept of virtual markers, which basically means adding markers to the stick figure on identifiable places that would also be identifiable on the musculoskeletal model, and using this to actually drive the musculoskeletal model from this data. And this is also something that I referenced one paper in the end that you can check out if you like. But in this version 7.2 and beyond, this is quite an automated procedure now in Anybody. Furthermore, we used the ground reaction force prediction tool embedded in Anybody, which has also been evaluated quite extensively by now for activities of daily living and for sports-related movements, also, and specifically with inertial motion capture as well. And we also evaluated, of course, in our evaluation experiments during lifting. So another thing that we did not measure was the boxes that were actually lifted in the supermarkets. So of course, this was because it was quite, we were under a lot of time pressure, and it was also, we were doing this during opening hours most of the time. So we had to be quite sleek in the way we obtained the measurements. But that didn't allow us to put any IMUs or anything like that on the, or we chose not to, at least, on the actual boxes. So instead, we chose to drive the box kinematics by the position of the hands. And also we added a constraint in the sense that if you see these 2 little green dots on the boxes on the right side, on the model at least, and to determine the or control the movement in the sagittal plane rotation, we said that these 2 points on the boxes should had the same distance to the ground plane at all times. And of course, this is a bit of approximation, but it is very closely resembling the actual process of lifting in the supermarkets. Also, we added some muscle-like contact elements at where the hands meet the box, basically to create actuators for these additional degrees of freedom that are introduced. And in this way, we were able to solve the inverse dynamic analysis. So here are some examples from the study. So on the left here, you see low to low handling of milk, while on the right, you see the high starting position and high shelf height. And I need to mention that like the low and high, or even mid, even though I'm not presenting it here, there's also a medium shelf height. these are not the same for all the merchandise, like because milk would only be stored in certain places, same for bananas and so forth. So what you see here is specifically for the handling of milk. But you can see that it involves taking it from the transport cage, rotating and walking a little bit to be able to place the milk at an appropriate place in the shop. And you can also see quite clearly here how the prediction of ground reaction forces is worked while these contact nodes is coming into contact with the ground plane. They actually estimate the ground reaction force. You can also see the activation of the contact nodes on the hands as well. And even more like some activations of the muscles as well. Like you can see that with the color configuration here. Another example would be bread, again here from a very low starting position to a high starting position above shoulder height. And this basically resembles, so bread could be stored many different places, both low at waist height and above shoulder height as well. But you actually see quite like a big range from the start to the end. Like they have to carry the box quite a while, and again it involves walking and carrying. And so it's here where this kind of technology is quite valuable, because this would not be able to be measured with many other of these more traditional lifting tools. So of course this is something that is quite an advantage of using this kind of methodology. So here are an excerpt of some of the results of we have, of course you saw there is a lot of lifts, so we also have a lot of results, and we chose to focus on the compression and shear forces at the L5S1 joint in the lumbar spine, and also the resultant glenohumeral joint reaction forces and the knee joint reaction forces. So basically the joints that are mostly involved when you do a lift of this sort. So what you can see here is basically the lifting cycle from 0 to 100%. And if you here you have these two levels of the lumbar spine, the L5S1 joint and L4, L5. And basically you can see the whole, what you call it, the whole cycle of the lift, and you can see the compression force, how it develops from it peaks kind of when you pick up the weight, and lowers a little bit when you walk with it, and has an additional peak when you place the lift again. And what we normalized it to body weight, so you see this percentage of body weight. So for a milk, this almost results in a 5 times the subject's body weight compression force. If we move on to the other example I took here is bread. So this was a bread low to high. Again, here you have the L5S1 compression and shear forces. So again, about up to 4 times the subject's body weight, while the anterior posterior shear force reached about 101 to 1.5 times the subject's body weight. And I might add that, of course, for people who worked in ergonomics or with ergonomic science before, these are the two main variables that has been used traditionally to assess the risk of injury during lifting, or injury to the back specifically. So of course, these are one of the things we have been the most interested in analyzing. Another thing you can see here is when you move this bread from a low to high starting position, the joint reaction force in the shoulders increases significantly. And there are particularly 2 cases. One was the handling of bread, another the cucumbers, where the joint reaction force in the shoulders increased quite a lot, like relatively to all the other merchandise that we measured, reaching almost 2 times the subject's body weight. In the lower right corner, you have the knee forces. A little bit higher variation here because, of course, we didn't restrict the subjects in how they would handle the lift. Besides, we gave them a starting position, we gave them end position, and we also asked them to keep both their hands on the merchandise. And this was mostly for modeling purposes. But as you can see here, people, if they took it from one side on the other, or they took one step with the left or one step with the right first, this creates this variation in the data. But here it's up until about 5 times the subject body weight, but for the heaviest lift, we saw almost 8 times the subject's body weight in the knee resultant joint reaction force. Another main finding here from the study was that when you take these estimated compression forces and anterior-posterior shear forces in Newton, you're able to compare them to the tolerance limits or biomechanical tolerance limits proposed in the literature. And the two most well-known, I would say, and most used are the compression tolerance limit first proposed by NIOSH of 3,400 Newton. This is something that, of course, is based on both in vitro studies of spinal compression, expert consensus, and also studies where you have some estimation of the load of a lift, and you can kind of relate that to the prevalence of low back pain in a certain population. For the anterior-posterior shear force, also these there's a good review by Gallagher and Maras going through all these in vitro studies of shear tolerance for spinal units, when they also propose a shear tolerance limit of 1,000 Newton. So basically what you can see here from the merchandise work tests that we measured, a lot of these work tests actually exceeds these tolerance limits, even though, like, relatively speaking, maybe if you can compare it to other industries, a weight of 20 kilos might not be that much, like, because I know there are many other industries where you lift more often, but using this tool, we can actually see that even like 20 kilos or milk, which was 17 kilos, or even cucumbers, which was as low as 10 kilos, but when lifted to a low to high position, also exceeds these tolerance limits for compression. And we use the upper confidence, 95% confidence limit in this case. When you look at the anterior-posterior shear force as well, the same things here. Bananas, milk, also cucumbers and bread, especially when these are lifted from or lifted to a low starting position. So basically, our main findings is, well, first of all, we're the first study to estimate dynamic spinal loading based on field measurements. So of course, this is both a risk assessment study for this group of workers that we investigated, but it's also a kind of a proof of concept to show that, yes, we are now at a place where this can actually be done. Of course, this is still not perfect, which is I would get back to in one of the next slides. But we've shown that it can be done, and we are quite excited about the potential of using this technology in ergonomics. So based on this study, we found that some merchandise, specifically bananas, milk, and cucumbers, exceeded the well-known tolerance limits in the literature and therefore could pose a risk for the development of low back pain and injury. We also found that both weights, the start and end positions, they all had a considerable influence on spinal forces, which of course is important to know when you need to do a redesign of the work process, that you can change a lot of parameters or a lot of ergonomic factors, you can call it, to try to decrease these hazardous loads. Another one was this lifting cucumbers, which is a relatively light merchandise to high shelves, resulted in the highest shoulder forces by far. And also that the weight of the merchandise was the main predictor of high knee forces. So high knee forces was not really dependent on the start or the end position, at least the resultant knee forces. But of course, as I mentioned before, when lifting, for example, heavy merchandise and walking with it, there are some point where you are putting all of your weight on one leg, which can result in up to 8 times the subject's body weight in the resultant force in the knee. So just to briefly discuss some of the practical implications that or practical advice you can give to the industry based on a study like this. So first of all, we would suggest that the handling of milk crates and bananas should be avoided whenever possible. And it could be avoided in the sense that there's how they receive them from the actual producers can be changed if there's enough can say motivation or will to do so, or it can be repacked and handled one at a time or in a different way when they actually reach the shop. And for example, bread, cucumbers should only be placed below shoulder height or stocked individually, so you would avoid these relatively high shoulder forces. And I say this because this seems like a reasonable thing to advise, since the shoulder forces were much higher, in the sense of twice as high as the next merchandise we measured. So of course, here you also have the possibility to repack or stock individually or something like that, or lower the shelf, for example. And brings me to the next point. The high shelf could be lowered to avoid working above shoulder height. So of course, here I showed some of the kinetic results, but there are of course a lot of kinematic results as well. And we found that a lot of these work tests that were in the supermarket sector involved working above shoulder height. And working above shoulder height is quite a well-known risk factor for the development of musculoskeletal disorders as well. Technical assistive devices could be used to limit hazardous exposures, and it's something you see some supermarkets use them quite consistently, others don't use them at all. But especially here where you have these particularly hazardous lifts, for example, bananas and milk crates, or you have a very high shelf and you insist, because of space limitations in a shop, for example, you would insist that it has to be put up there. Like, you can use technical assistive devices for this purpose. Also, another thing could be that you should consider individual factors in relation to job demands. And what made me make this recommendation is basically also a nice review done about the compression tolerance of spinal units, and where they see that there's actually a quite big of a difference in the compression tolerance of the spinal units and individual vertebrae for different age groups, and also between men and women, and also in different in just health status in general. So of course, when you plan the work in a supermarket, it would be a good idea to take some of these things into consideration and how you assign work tasks to your different workers. So some of the limitations of this technology here. So in the evaluation study, we actually found that the trunk forward flexion angle relative to the pelvis was considerably underestimated, which also means that the anterior-posterior shear force is considerably underestimated. So of course, this is something to keep in mind when looking at the data from this study, which also means that many of these merchandise could actually pose a risk for the development of low back pain, even though our study did not show it, at least for the shear force. So this is important to of course keep in mind. The reason for this underestimation, it could be many reasons. Of course, there has a lot less detail available for when you're in the different motion analysis equipment. Of course, if you have markers, you have 4 markers on the pelvis, more on the spine, sternum, clavicles, and so forth, which can give you quite an accurate representation of the kinematics of the upper body. And in the XSense case, you have 1 IMU on the pelvis, and you have 2 on the shoulders, basically. So there's not a lot of information to actually estimate this this angle here. And also, one thing to mention is also that the placement of the actual IMU on the XSense system is a little bit tricky, because you put it on just over the sacrum on the pelvis with this band, basically you attach around the subject, and it has a tendency to move around a lot, especially when you bend forward and lift something. So this is also something, if people other people would try to use this for analyzing lifting, it's something to be aware of, that you need to continuously correct where the pelvis IMU is placed, basically. Another thing can also be, there was also quite an error in the estimation of the kinematics of the foot. Basically, the subjects would stand a lot more on their toes and flex their knees more compared to the marker-based system, at least in the laboratory experiment. It already looked better when in our data sets, I must say. So I would think or hope that like this error has been reduced somewhat in the data set we have, but at least in our evaluation, that was also an error that could have contributed to this. So, and in its present form, also this methodology is quite time consuming. So using ergonomics, of course, time is a factor usually, and you don't have a lot of time to give answers, and a lot of people in the industry don't have the same patience as maybe a scientist would have. But even though, like now, we went through a lot of the problems that could arise when using this kind of technology, and I'm quite convinced that this would be easier as time passes and as limitations are identified. The approach of using this kind of technology will be a more streamlined than it is in its current state. Another thing is, of course, to remember that this kind of method only estimates acute loading, so loading during one lift, for example. But we also know that in the supermarket sector, accumulated loads are quite important because often they would have an 8, 10, 12-hour shift where most of this time they would be involved in some kind of manual handling. So of course, there's also a risk of injuring yourself if you keep on lifting even lighter loads for an extended period of time. But this is, of course, something other methods, more physiological or psychophysical methods, would be better at estimating. Lastly, I have already mentioned a little bit some of the possible errors in the kinematic data from the Xsense motion capture suit. And here specifically, we found that there was errors in the position of the hands. So this means that especially when we were analyzing lifts which involved like very narrow small boxes, because of there was an error in the estimation of the hands, sometimes the hands would even be almost on top of each other, meaning that the load would not have the correct position at all, which actually meant that we had to exclude most of these types of trials. Another one is that in this case, there seemed to be an excessive amount of palmar dorsiflexion of the wrist. And did actually led to some kind of unforeseen errors in the muscle wrapping of the wrist flexors. So, and this was quite a challenge to try to resolve. So it actually also led to the exclusion of all the one-handed lifts that we analyzed. But as I heard from anybody in the new release, there should be a new experimental wrapping algorithm that should actually have what you call it. Yeah, these errors should have been resolved somewhat at least. I'm very hopeful that it is completely resolved. So possibly the next study using this kind of methodology should not be so worried about this problem. So here to last points. We believe here that estimating dynamic joint loads based on field measurements is a great leap forward, because you have, first of all, you have an abundance of information providing quite valuable reference material for both the scientific community, but also for industrial stakeholders. You have many muscles, you have quite accurate joint definitions, and you're able to get knee, ankle forces, low back forces, shoulder forces in one go. So it's all kind of an all-in-one biomechanical analysis here. And we also believe that here we are talking about a much higher accuracy, or is much closer to a real life than it would be if you used 2D static or quasi-static analysis tools. Of course, there's still some issues that needs to be resolved, especially some of them I already mentioned earlier in the presentation. But we believe there's a great potential for using this this technology for ergonomic analysis of different work tasks. So that was it for me, and thank you for listening in.
So thank you very much, Sebastian. I will just make myself the presenter again and show my screen. Yes, so thank you very much for the presentation, Sebastian. I would just like to say a few words regarding our online resources before we go to the Q&A session. And first of all, if you want to know more about the Anybody technology and the Anybody modeling system, then please go and check out anybodytech.com, where you'll be able to find special dates and events and a full publication list. You can also check out our website called indyscript.org, where you will find the community website for people using Anybody. You can find the full wiki page and link to the different repository sites. And here's also the forum located. So if you need some help from some fellow Anybody users, you can go there and present your question. And if you have any question regarding starting modeling with the Anybody modeling system, or you just want to meet up, then please feel free to send us an email at sales@anybodytech.com. And if you're already using the Anybody modeling system and you have created something really interesting, then please send me an email and we'll try to figure out how to make you present your work in the future. Yeah, and Sebastian already told a bit about it, but the Anybody modeling system version 7.3 has been released a few weeks ago, and it includes the updated model repository called the AMMR v2.3, which includes a large-scale gait mockup example. And it also includes a new and faster experimental wrapping algorithm, which is 5 to 100 times faster than the old one. And it is inspired by the work of Lloyd, Stockness, and Fels, 2019. And all in general, there's some faster load and simulation time, and the load times for models is reduced by up to 25%. Then we have improved the model view performance as well, included a new class list and a new reference manual. But if you want to see more or read more about this, then I have provided the link below here, and when we upload the presentation from this webcast, you can go and check it out.